is what I kind of did for the way back when we did titrations. I like to kind of write under the species of this balanced chemical equation what we know about. For hydrogen, if you read it, we know the volume, the temperature, and the pressure. We don't know moles of hydrogen. What we're trying to get to is the volume of ammonia. Ammonia, it says it's a STP, of course, that stands for standard temperature and pressure. Standard temperature is 273.15. Standard pressure is 1 atmosphere. So, of course, we don't know the number of moles here. But what you're going to see on the next few slides is something kind of we did in stoichiometric calculations. We can use moles of this. We can use P equals nRT, rearrange it and solve for N for our H2. And then we can go ahead and use stoichiometry once we have moles of this to get to moles of this. And then once we have moles of this, we can go ahead and get to volume of that. But there is kind of a trick to get from moles to volume that won't have to use P equals nRT. So that's what you're going to see. We're going to focus on our hydrogen because that's what we know the most about. We did one of these kind of on Friday. So we're going to solve for N. We divide both sides by RT, and it looks like this. N is equal to PV over RT. And in that little box there is what we had in the given earlier. So we're just going to plug and chug. So N is equal to PV, that's 0.783 atmospheres, also in the numerator, volume 125 liters. In the denominator, we have RT, that 0.082058 units of R are liters, atmospheres per mole Kelvin. And then we also have temperature in the denominator, which is 298 Kelvin. So notice the units that cancel. Atmospheres cancel. That's the most exciting part of these problems. Liters cancel. Kelvins cancel. We have the inverse of moles in the denominator. So kind of resolving the situation, that means actually taking it from that ratio from the denominator to the numerator. We have units of moles, which is awesome. 3 sig figs, you're looking at a nice round number, 4.00 moles of H2. So we're kind of filling this out as we go. You wouldn't have to, but in my mind, that's kind of what we have. Now we can use stoichiometry. Of course, we have a 2 moles to 3 moles relationship. We've done a lot of these earlier. So my next thing, you're going to see the first term, 4.00 moles of H2 over 1. And then I'm going to use a stoichiometric ratio. I want moles of H2 to cancel. I want to be left with moles of NH3. So it's going to look like, I can't tell if you guys are ready. It's going to look like this. So we take our 4.00 moles of H2. We take it times the stoichiometric ratio. That 2 moles of NH3 for 3 moles of H2. Those came from the stoichiometric coefficients. Remember, those 2 and 3 bring no uncertainty, so we're still allowed 3 sig figs. So you end up with 2.67 moles of NH3. So 2.67. The screen's showing up. Okay. Now, if we wanted to, we could go ahead and rearrange the P equals nRT, solving now for volume. And we could go ahead and plug into that. But I want to do something a little bit different. The fact that this particular problem says that your NH3, your ammonia, is at standard temperature and pressure, I want to make use of that fact. So again, part of my problem as a teacher is knowing that there's different ways to skin a cat, actually meaning a catfish. But instead of going back to the ideal gas law equation, I want to revisit that standard temperatures and pressures, standard temperature and pressure. We know that 1 mole of any gas is going to be equal to 22.414 liters. You could write that on your sheet if you wanted to. And we're going to use that to our benefit. So we know that we have 2.67 moles, and if I use that equivalency statement as a conversion factor, it will look like this. 2.67 moles of NH3 over 1. I want moles to cancel, so I'm going to put 1 mole in the bottom and that 22.414 liters in the numerator. So that's just kind of a quicker way, I think, than using P equals nRT to solve for V. But you could have done it either way. So we need to round to 3 significant figures. Of course, moles will cancel. We're left with units of liters. So then the answer to this problem is 59.8 liters of NH3. It's actually a lot. So that's that. Okay. Another problem, one more problem in this part. And my pen works. So actually, I'm gonna write under there, I think, a little bit. I put new batteries in it. So, all right. Notice that for hydrogen, I've got V is equal to 25.0 liters. My T is equal to 25.0 degrees Celsius. And I say to myself, oh man, if I'm using R, or actually even if I'm not using R, I'm going to have to convert that to Kelvin. Pressure is equal to 1.25 atmospheres. Okay, that's my H2. Then it says nitrogen's excess, and we kind of have an idea of what that means. That means any sort of stoichiometric calculation is going to be based on my H2. Now, down here's the question. It says how many liters of ammonia, so I'll put under my NH3, I'll put V is equal to question mark. Measured at, now this is my ammonia, is going to be at 25.0 degrees Celsius, and my pressure is going to be 1.25 atmospheres. Now, this problem was picked specifically. Hopefully, do you guys see that actually my gases I'm kind of going between with regard to a reactant and a product are at the same temperature and pressure. If they're at the same temperature and pressure, you're going to see on the next slide, I can use Avogadro's relationship with regard to gases, that the volume is directly related to the moles. And how do I know moles? I know relative moles from the stoichiometric coefficients. So I'm going to use that to my benefit. I'll show you what I mean. I could put another way. I could go ahead and use VTP and get to N. And once I have N, I could go ahead and use stoichiometry to get to this N. And then I could plug this N here using PV equals nRT to get to V. I could, but I'm not gonna. Okay? I'm going to use the fact that since pressure and temperature were held constant, I know that from the stoichiometry, 2 moles of NH3 will be produced for every 3 moles of H2 consumed. I also know then 2 liters of NH3 will be produced for every 3 liters of H2 consumed. Okay? So it's a special case since the pressure and the temperature were the same. So with that in mind, I can go ahead and just use, I was given volume, this is a different problem, but a minute ago I was given the volume of the H2. I can go ahead and just use this ratio right here on the right and plug and chug. So we were given 25.0 liters of H2, and again, I can use that ratio. Relative volumes are related to moles as long as pressure and temperature are the same. Okay, liters of H2 will cancel. I can do that math in my head. No, I can't. I was thinking the units cancel, but the numbers don't cancel. I would use a calculator for that. So units of liters of H2 cancel, we're left with liters of NH3. Rounding ourselves to 3 significant figures, we get 16.7 liters of NH3. Again, could you use PV equals nRT a couple of times and get the same thing? Oh yeah. But this is just a little quicker. A little slicker. Okay. Ooh. All right. So this is my little warning that that little tool trick we just did only works if your pressure and temperature were constant, which they were. Okay, so we've kind of got this reoccurring theme. Your Alta homework looks like it's due Thursday. Okay. To get the extra credit, you're going to want to do it by Thursday. So on to part 4. Hopefully. This is so nice to have my little pen working again. Okay, this is a fun thing. The kind of the concept of having a gas mixture and knowing that all of those gases in the container, the mixture, actually are exerting a pressure. So we've talked a little bit about, in this room, you're about 80-20 mix of nitrogen and oxygen. So if I could see those nitrogen, oxygen gas particles, they'd be, I wish I could see them, they're just bouncing around. They're both bouncing around. Actually, there are traces of other gases too. Okay, but there is a pressure brought by the nitrogen and a pressure brought by the oxygen. So the idea, the concept of a partial pressure, like in that case, would be we have a pressure of the nitrogen and a pressure of the oxygen. The way we kind of denote that would be, we do like, this is P, obviously, for pressure. If I was talking about the nitrogen in the room, I would call that the partial pressure of nitrogen. Okay? And actually, we have a partial pressure of oxygen. And if that's the only two gases, what do you think that subscript T stands for? Total. Yep. And it's a cool concept. It totally makes sense. Whatever bang your nitrogen's giving you, added to whatever bang your oxygen's giving you, actually collectively creates a bang for those gas particles. Makes sense. So this is kind of showing you how that would work. We've got three gases here. We've got a gas A, which is this partial pressure, gas B, this partial pressure, a gas C, that partial pressure. And it's just like I described. So actually these three gases are in the same volume and they're at the same temperature. I am somehow going to transfer the contents of those three gases into a single container with the same volume. Okay? And notice it's so cool. I have the blues and the purples and the yellows all in that far one. If I were simply to take, and of course kPa stands for kilopascals, if I were simply to take those three pressures and add them together, I get 1,350 kilopascals. Makes sense. I love it. Okay? So I've got a little bit more to kind of talk you through. I'm going to do a similar thing here with those three canisters. I've got a canister over here to the far left. That's where I'm going to be where I'm going to put everything. Okay, notice that those four canisters, the three canisters with the components A, B, and C, and the canister over here to the right where I'm going to dump everything, they have the same volume and they're at the same temperature. Okay, and I don't know, I try to kind of fix my slides as I go, but I would call that a P sub T up there. P sub T for total pressure. N sub T stands for total number of moles. So here are my components. Okay, oh, by the way, I'll put a little subscript T here. My total pressure is equal to the total number of moles times R times T divided by V. Just rearranging P equals nRT to solve for P. Okay, here are my components. Oh, by the way, then down here, yeah, the total number of moles are the moles of your individual components all added together. So here are my individual components, component A, B, and C. I have moles A, B, and C. I have partial pressure A, partial pressure B, partial pressure C. I could go ahead and for each one of these calculate the partial pressure from P equals nRT, and it would take on the same form, but instead of the total pressure, it's the partial pressure of A. Instead of the total moles, it's the moles of A. But notice in all these cases, R is the same, temperature is the same, and volume is the same. So I can do the same thing for partial pressure of B, partial pressure of C. I'm kind of running you through building up to kind of a proof to what's called Dalton's law of partial pressures, which there's a lot of laws in, or a lot of, yeah, I guess they'd say laws in science. I'm like, really? That's a law? That's like a no-brainer, okay? Okay, so I'm going to put a little subscript T up here. The total pressure is equal to the total number of moles times R times T divided by V. Now, we can go ahead and distribute through N sub T is equal to moles of A plus moles of B plus moles of C. And then I can go ahead and break this out. Oh, gotta put my little total pressure there. I can break this out into this, where the total pressure is equal to moles of A, RTV, plus moles of B, RT divided by V, plus moles of C, RT divided by V. Well, you know where I'm going with this. because each one of those three quantities added together on the right, actually, that's equal to the partial pressures of each of them individually. Dun, 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 yay, Dalton. We have come up with Dalton's law of partial pressures. Dalton said that if you have multiple gases, in this case, gas A, gas B, and gas C, they're all banging around in the same container. They actually, their pressures are additive, basically. That's it. That's totally it. Okay? Dalton's law of partial pressures. Shouldn't give him such a hard time. He was early, 1700s? He came up with the atomic theory, too. And I guess he was colorblind. A tutor in England. Okay. So let's see, hold that thought. Let's see what we can do with this. So I'm going to put a little T here. I know I don't fix my slides because it's a pain in the butt to kind of go back and I don't have the equation editor. But anyway. So I'm going to do something with Dalton's law of partial pressures. I'm going to kind of show you proof of something that's important. Have we done this before? I think we've done something like this before. Okay, we know this. Partial pressure of A is equal to moles of A times R times T divided by V. The total pressure of a mixture of gases is equal to the total number of moles times R times T divided by V. All right. What I'm going to do is take equation 1 and I'm going to divide it by equation 2 on both sides. So it kind of looks like this. There's equation 1. There's my divisors. There's equation 2. Okay, so I end up with this ratio is equal to this ratio. Now, the cool thing about that is, check this out. My R and T cancel, my V cancel. So guess what? Okay, so it kind of ends up looking like this. The partial pressure of A divided by the total pressure is equal to the number of moles of A divided by the total number of moles in the gas mixture. Well, if we rearrange that a little bit, we get something that looks like this, where the partial pressure of A is equal to the moles of A divided by the total moles of gases in that same container, times the total pressure. So we're all about variables in science. So actually I'm going to take this ratio quantity and I'm going to give it a variable. Here we go. We use the symbol X to represent what we call mole fraction. See right here where it says mole fraction? Mole fraction. So X is mole fraction. If we've taken the fraction of something, we're taking how much there is divided by how much there is of that thing of interest divided by the total much of what there is, okay? So mole fraction is the moles of A divided by the total number of moles there. Okay, that's mole fraction of A. So we can restate that little equation I had a minute ago by saying the partial pressure of A is equal to the mole fraction of A times the total pressure. You see why I think the subscript T's are so important? I think they are. So when I'm working a problem, that's what I'm thinking. Makes sense. Okay, so we're going to see how that works. Mole fractions we've dealt with before in talking about how concentrated a solution is. Mole fraction, remember that? Mole fractions can approach 1, but they'll never be greater than 1. Mole fraction of 1 means that it's all one thing. Okay, they'll usually be like a decimal number. So what that's saying is the partial pressures of anything should always be less than the total pressure. Okay, unless there's only one component in which the partial pressure will be the total pressure. Okay. So put in so many words, partial pressure of a gas is directly proportional to the mole fraction of the gas. Okay. So let's work a problem. I think I will go ahead and put this one on the board too. That seems to be looking good. Here's my box. And I think I've said throughout the semester, one of the things of drawing something is it helps you settle, and you can stall. So I've got 3 components in here. I have, and I can go ahead and show they're bouncing against their container. I have 2.00 grams of carbon dioxide. I have 2.00 grams of nitrogen. And these are all gases, obviously. And then I also have 2.00 grams of neon. They're all gases. They're all banging around in there. So we have some information about the container. The volume of the container is 5.00 liters. We know the temperature, although I bet we're going to have to convert that to Kelvin here in a minute. We know the temperature is 15 degrees Celsius. And we know that we have this relationship, PV is equal to nRT. And more recently, you might want to put this on your note card for the exam and kind of understand how to use it. We said the partial pressure of anything, for instance, the component A, is equal to the mole fraction of that component times the total pressure. All right. So in italics down there, we're supposed to come up with the partial pressure of each gas. So partial pressure of CO2, the partial pressure of N2, and the partial pressure of, we can do this, of Ne. Okay? And they were all also supposed to come up with the total pressure. Now, we could do it in this order, come up with the individual pressures, okay, and then add them together to get to the partial pressure, but I'm not going to do that. I'm actually going to go back up to my PV equals nRT, and I'm going to recognize that the total pressure is equal to the total number of moles times R times T divided by V. That is going to save me a few steps, and from what I know of y'all like saving a few steps. So what you're going to see on the next few slides is I am going to use the molar masses of everything, to get to moles of CO2, moles of N2, moles of Ne. Then I'm going to add these together to get to total number of moles. And then I'm going to plug that into here. And actually, I'm going to get that guy first. Once I have the total pressure, I'm a hop, jump, skipping away of getting the partial pressures of each of the components using their mole fraction. So that's what you're going to see. So we need to get the individual moles, and it looks like this. The molar mass of carbon dioxide, when you guys were doing your combustion analysis, 44.01 grams per mole. So we're going to take 2.00 grams of CO2 times 1 mole over 44.01 grams, 3 sig figs, that will give us 0.0454 moles of CO2. We're going to do a similar thing for nitrogen, of course. 1 nitrogen is 14.01, so 2 nitrogen is 28.02. So we're going to take 2 grams of nitrogen times 1 mole of nitrogen over 28.02 grams. 3 sig figs, you're looking at 0.0714 moles of N2. And then we just need to go to the periodic table and look up for neon. 20.18. So 2 grams of neon times 1 mole of 20.18 grams. 3 sig figs, you're looking at 0.0991 moles of neon. So again, we could use these individual moles, and we could come up with the individual pressures by now plugging in PV equals nRT, because we have volume and we have temperature, and of course we know what R is. But why? And actually I want to emphasize a way to use the total pressure to and this equation to get to the partial pressure of each of them. So like I said, on the next slide you're going to see these all added together. So adding these together, you get, remember, since we're adding, we round according to decimals, and we got 4 decimal places in each of these. So we are allowed 4 decimal places. So your N sub T, your total moles, is 0.2159 moles. So that's what I'm going to plug in here. Okay. All right. So P equals nRT. Don't let this catch you. That we arrange it. We get pressure by itself. We divide both sides by V. Okay. And my I'm going for total here. So actually, like I said, I would kind of consider a subscript T here for the P and a subscript T here for the N. So total number of moles is at 0.2159 moles. We do have to fix the temperature by adding 273 units. Give us 288 Kelvin. Volume's fine, it's in liters. So down here now, the total pressure is total moles, 0.2159 moles, times R, 0.082,058 liters atmospheres per mole Kelvin, times T, which in Kelvin scale is your 288 Kelvin, divided by the volume, which we said was 5.00 liters. Looks like we're only allowed 3 sig figs by both of our temperature and our volume. So that means, and units of course would be atmosphere, because moles have canceled, liters have canceled, kelvins have canceled. Atmospheres. 3 sig figs, you're looking at a total pressure of 1.02 atmospheres. So again, and actually this definitely happens in physical science problems. We're not going for this first, we're going for this first. All right. So that answers that. Now, we can come up with the partial pressure of those 3 gases if we take that number, the total pressure, times its mole fraction. And remember what mole fraction is. Mole fraction is the moles of the component divided by the total moles. So here we go. Taking on carbon dioxide first. A few slides ago, we came up with the moles of CO2 was 0.0454. We just now, a little bit ago, came up with the total moles with those 3 gases, 0.2159. So that gives us the mole fraction. I'm going to put a little subscript T with that pressure. The total pressure we said was 1.02 atmospheres. 3 sig figs, that gives you the partial pressure of CO2 is 0.214 atmospheres. Nitrogen, we're going to do a similar thing. A few slides ago, we came up with the partial pressure of nitrogen, 0.0714 atmospheres. The total pressure of all 3 gases, 0.2159 atmospheres, again. Also, then I said total pressure, total moles of gases, 0.2159. The total pressure, 1.02 atmospheres, 3 sig figs, you're looking at 0.337 atmospheres. Now, sometimes students at this point will say, hey, Mrs. Snipes, I bet I can take the total pressure, which was that 1.02 atmospheres, subtract these 2, and I can get neon. And you would be right. We're not going to do it that way. A few slides ago, we said the partial pressure of neon. A few slides ago, we said that the moles of neon was 0.0991. We said the total moles of those 3 gases was that 0.2159. That'll give us our mole fraction, that ratio. We said the total pressure of all 3 gases is 1.02 atmospheres. Again, we're limited to 3 sig figs, so you're looking at a partial pressure of neon of 0.468 atmospheres. Cool. So yeah, adding those 3 together, you should get your 1.02 atmospheres. plus or minus a little bit. All right. Let's do another one. They just keep coming. I'm going to go ahead and write under the equation what we know about this. Now, don't let this throw you off on your final exam. That actually, what does the L stand for here? Liquid. Does liquid follow PV equals nRT? No, does not. Again, that's a hint. You'll be like, I know she said this is somewhere on this final exam on Friday, but yeah. Let me go ahead and kind of clear the board here. So in this case, here's our box. We have two liquid reactants. I'll just put it R1, which is a liquid, and R2, which is a liquid. We're gonna put them in our box, which is kind of exciting. Notice it says that of the first reactant, we're gonna have 150 with 3 sig figs grams of that liquid. It says it's gonna react completely, and we're gonna have excess of the other reactant. So that's good, because so we know we can do stoichiometry based upon the first reactant, the dimethylhydrazine. And we're going to collect the gases all together in that box up there. It gives me some information about the gases. So all 3 of these gases are collected. My temperature is 27 degrees Celsius. Again, we got to fix that to Kelvin. Heck yeah. It gives me a volume is 250 3 sig figs liters. Okay, cool. So we are supposed to come up with, so question mark. Well, I don't think I'll put it under my, yeah, maybe so. So question mark, this is the first one. The total gas pressure, so P sub T, okay? And then also, we're supposed to come up with just the partial pressure of one of the products, N2. So picture this, if I could make, you know, here's one gas with these X's. One gas is these circles, okay? And one gas is these bullseyes, okay? So we have a gas mixture in here. We have 3 gases in there, and that's what they are, N2H2 and CO2. So do you see where I can use, it's kind of one of the things we've already been talking about, I can use those grams to get to moles, right? No problem, using the molar mass. Easy, easy peasy. And actually, I'm going to do it, how do I say this? I could use those moles then to use stoichiometry to get to the moles of N2, the moles of H2O, and the moles of CO2. Oh, by the way, what does G stand for? Gas, yep. So all of these things, like I kind of put on the board, are going to be banging around in there. Don't let that throw you off on your final exam. Okay, so those 3 things are going to be banging around in there. I could come up with the individual pressures, add them together, and get my total pressure. Of course, along the way, I would have gotten my partial pressure of N2, okay, just by using PV equals nRT. But I'm going to do it a little bit different. So, do you guys buy this? Well, first off, I'll show you my trick here in a minute. For sure, we need to use that, the 150 grams of dimethylhydrazine to get to moles. So if you came up with the molar mass of dimethylhydrazine, you come up with 60.10 grams per mole. We've done this a lot in Gen Chem 1, where we can use the mass of the compound, 150 grams, 3 sig figs, use the flip of the molar mass, so we have 1 mole per 60.10 grams. Grams cancel, leaves us with moles of the reactant. 3 sig figs, you're looking at a nice round number, 2.50 moles of dimethylhydrazine. Do you already have that slide? No. Okay. So here's my trick. Those moles actually are going to create 2 moles of N2, 4 moles of H2O, 2 moles of CO2. So do you buy this, that collectively, if you add 3 plus 4 plus 2, you get 9. So collectively, for every 1 mole, because the stoichiometric coefficient in front of dimethylhydrazine is 1, for every 1 mole of that reactant, you get 9 moles of gas produced. I'm going to use that to my benefit. Here we go. So we said that in that 150 grams of reactant, we have 2.50 moles of CH3 N2H2 dimethylhydrazine. I put that over 1, and then I can simply bring down this ratio right here. 9 moles of gas produced for every 1 mole of dimethylhydrazine. CH3 quantity 2, N2H2. No uncertainty brought by the 9 and the 1, so I'm allowed 3 sig figs. So you're looking at a total, so that's my NT. This guy right here, that's my NT. Total number of moles produced. So we know we can find a total pressure from the total number of moles like that, and using the volume and the temperature that was given in R. That's exactly what I'm going to do. Okay, so rearranging P equals nRT, we know that P, the total pressure, is equal to the total number of moles times R times T divided by V. So here we go. Oh, we need to fix our Celsius temperature, so it was 27 Celsius, so we can add 273 degrees, and you're looking at clear 300 Kelvin with 3 sig figs. Of course, the volume was given, 250 liters. So now plugging in, again, I'm going to put a little T subscript next to that P. The total pressure, which is one of the things we're supposed to find, is equal to the total number of moles, which was 22.5 moles, times R, 0.082058 units of R. With that value are liters atmospheres per mole Kelvin. The Kelvin temperature was 300 Kelvin. Then in the denominator, we just have the volume, which was that 250 liters. Rounding to 3 sig figs, you end up, and units will be atmospheres, you end up with 2.22 atmospheres. Now, from that pressure, we're supposed to, one of our things was to come up with the partial pressure of just nitrogen. So actually, we're going to use this to our advantage again. The partial pressure of anything is equal to the mole fraction of that thing times the total pressure. So we need to get to the mole fraction of N2. So we need the relative numbers of moles of N2 to the total number of moles. So actually, again, if we look back at the moles that are produced, we said there's 9 moles produced. Of these 9 moles produced, 3 moles are going to be nitrogen. That's my mole fraction. 3 moles of N2 and for every 9 moles total. Now I know we could go ahead and divide and we get 1/3, but I'm going to go ahead and leave that ratio the same. I'm going to go ahead now and bring back my total pressure. The total pressure we said was 2.22 atmospheres. The total pressure we said is 2.22 atmospheres times the mole fraction, which for nitrogen it's a 3 to 9. So this is the total pressure. And that's the mole fraction. Okay, 3 sig figs, you're looking at a partial pressure of nitrogen is 0.740 atmospheres. Again, there are ways to work this problem other than how I worked it, but that's probably the best way to work it. There's some types of chemistry problems where you're like, oh, there's so many ways to work this. One of them is solution concentration, and another is acetic gases. So this is how far I wanted to get. I'm going to actually pick up here on Wednesday. And we'll finish this part, and we'll finish the next part on non-ideal gas behavior. And then we'll call it a semester as far as lecture goes. That's Wednesday. Thursday, we are back in the lab for something that you're gonna do the calculations on while we're there. Now, the lab, I'm not sure it's 15 or 16. I looked in I said, well, look at what I said it's gonna be. In my little roadmap, I said either 15 or 16. I've done them both, and I haven't decided. I will tell you for sure Wednesday. Yes,
What are
ma'am.
you doing? Is it still 11 o'clock on Thursday?
Yes,
And then 12 on Friday?
yes. That sounds right to me too. 11 o'clock on Thursday, 12 on Friday. And you get 2 hours, so 12 to 2 for your final.
And then I see.
And it's in here. Oh, it's in here. It's not in the other room. Yeah, it's in here. Because it's final exam, we don't have to pay for another room.
I can't stay for 2 hours. I have class at 1. No, you're not class canceled. Yeah, your class is canceled because that's why your test is on Monday.
It alternates, yeah. Your 1 o'clock classes their final will be on Monday.
It says like grade from when there's 10 points due to like the labs, right? Or is there anything to do with that? Because I think in the grade book says there's like 10 points.
For the ones that, the
Like
last.
it says it's just Friday, right? I think
I wonder if
that's
that's,
because I don't remember you giving us anything after the test, so I didn't know like you wanted to do for that.
I'll look for those, so this is labs, right?
Yeah,
Okay, yeah, you need to do Lewis, you need to do, nomenclature worksheet, Lewis worksheet.
Yeah, because he did that and
Yeah, that's great.
Oh,
And then actually in lab on Thursday, we will.
we'll have to write them. Okay.
Yeah, we will just.
Then that might be what that is. I just like seeing it. I'm like, did you hand me something? Was I supposed to do something?
No.
Okay.
Yay. Oh, and I do have I have your exams, girls, just a minute. Hey, yo, I brought your test just in case you showed up. Just so I can stop carrying them around. Yo. And then that's a few other things I handed out that might come in handy. There you go, Lindsay. You're welcome.
And so are you